So go ahead and start with that.
I was really scared last night. I had like a
All right, what do we got? First one,
1,
then
4,
9,
60, 25, 36, 49, 64, 81, 100, 121,
there you go. So those are going to be the most common squares that we're going to come across. I mean, you could carry on and go 13 squared is 169. 14 squared is 196. I mean, for lack of a better way, you could just say they flip-flop, 169, 196. 15 squared is 225. All right. Now this. Find the square of each integer from negative integer, integer from negative 12 to negative 1. First one. Negative 1 squared is 1. Recalling, if some of you, if you put this into your calculator, it will give you an answer of negative 1. It's because your calculator is not smart. You got to be careful with negatives. If you were to type in, just in your calculator, negative 1 squared, this is what your calculator is thinking. Your calculator is thinking negative 1 times 1 squared. When in reality, so again, this would be incorrect because your calculator is not smarter than you. Negative 1 squared is negative 1 times a negative 1. Negative times a negative is a positive. And then we carry on. 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144. All right. So when we're getting these, each of these are what we call perfect squares. 1, 4, 9, 16. So when we talked about difference of squares, when we do factoring, we're looking for these numbers. You know, x squared minus 36, x squared minus 64 would be, you know, if it would x squared minus 64, when we would factor that, it would be x plus 4, sorry, x plus 8, x minus 8, because it's a difference of squares. All right. But here we're talking about just straight up, it's a total square, 49. So with that being said, based on the work we did in the last two slides, what would we say the square root of 25 is? What number times itself is 25? Or negative 5. This will be 8 or negative 8. 11 or negative 11. And you're going to see this show up where we're explicitly told, remember the quadratic formula, solving for quadratics, x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. This plus or minus exists because when we take the square root, it could be a positive number or it could be a negative number, because negative 5 times negative 5, also 25. Whatever's in here, when squared, will be a number. That's why it was the plus or minus. Well, how about this one here? Square root of negative 4. What number times itself is negative 4? So again, as we said, 2 times 2 is positive 4. Negative 2 times negative 2, also positive 4. 2 times negative 2 is negative 4, but that's not a number times itself. So in this case, I'm going to split this up and make, instead of negative 4, I'm going to have it, wrong utensil, square root of negative 1 times the square root of, times 4. Right. 4 times negative 1, that's negative 4. I think we can agree on that. And here's the fun part about PEMDAS or PEMDAS. I usually write it with PEMDAS, where R stands for the radicals and roots, because we're now doing radicals and roots. When I am multiplying or dividing, roots and exponents can travel with them, but they can't when we add or subtract. What do I mean by that? I mean, this can be restated as the square root of negative 1 times the square root of 4. So when multiplying and dividing, that square root, I can split it up between two different things that are being multiplied. I cannot when I'm adding and subtracting, and we'll see that on a future slide here. So now I have the square root of negative 1 times the square root of 4. The reason why I split it up is because I know the square root of 4. The square root of 4 is plus or minus 2. So then I would have plus or minus 2 times the square root of negative 1. Do we know the square root of negative 1? No, we do not. The square root of negative 1, if you've not heard this in the past, the square root of negative 1 is defined as the letter I. What does that mean? Well, back in the day, when we talked about all our different types of numbers that we have, these are integers, right? And then any number that can be written as a fraction is called a rational number. Numbers that cannot be written as fractions, like square root of 2, can't write that as a fraction of integers. Pi, you cannot write pi as a fraction. Those are what are called irrational numbers. All of those numbers, integers, rational numbers, irrational numbers, are all considered real numbers. This is no longer a real number. So they have long time ago gave it the letter I to stand for imaginary number. Now don't let that confuse you. An imaginary number does exist, but just it was at the time when they were trying to call it like, well, if these are real, then the other ones must be imaginary. All right. Imaginary numbers, the letter I, if you ever get into electrical engineering, you're going to use I. Some of advanced levels in calculus, you're going to have applications where I exists. For the scope of this class, we won't talk about how this actually applies to anything other than plus or minus 2 times a negative 1. We're going to call this plus or minus 2I. All right. Graphically, if this were a parabola, because that's where we use a lot of these square roots, and we've been doing it when we're solving for a quadratic equation, this is finding my zeros. If I end up with this plus or minus 2I, that means I have my two zeros are what are called imaginary zeros. Graphically, imaginary zeros means if I were to graph this parabola, whatever my pretend parabola is here, it would be like this. I look and say, oh, does this ever cross the x-axis? No. Does it have any real zeros? No. Does it have two imaginary zeros? Yes, it does. So that's what it means. So graphically for us, it means there's no real zeros. The two zeros that do exist are imaginary zeros. That is, it does not ever cross the x-axis. So that's a little bit about how we're going to connect square roots with quadratics, with the quadratic formula, and how this moves together. I'm going to pause there. So now, again, looking at this order of operations, when we've talked about this, addition and subtraction are inverse operations. Multiplying and dividing are inverse operations. Exponents and roots are inverse operations. When we talk about the roots, the root has to be the same as the exponent. What do I mean by that? A square root, its inverse would be something squared. If I had a cube root, the inverse would be something, so here's something squared. Here it would be something cubed. So the only way that they are inverse operations for roots and exponents is if they're of the same base. Squared, square root. Cubed, cube root. Fourth root. So we look at what we have over here. I have something squared. And when I take the square root, I am left with just whatever that inside thing was. Because the squaring and the square rooting are inverse operations, they eliminate one another. Here, when I'm looking at square roots, all right, we know the square root of 9. The square root of 9 is 3. But it's not the square root of 9 anymore. It's 0.09. So when we go backwards, it's a matter of one of a couple different ways of going about this. I'll erase that 3 for a second. When we are looking at this as a decimal place, right? When we had here, then we had the tenths unit and the hundredths unit. Tenths and hundredths. So this is the same as the square root of 9 over 100. 9 100ths. Let me make sure my square root goes all the way down. Way back in elementary school when you learned, or at least were taught, if you remember it anyways, we have the ones unit right here. Then we have the tenths, we have the hundredths, thousandths, 10,000ths, and you keep on going. When converting this, 9 100ths, that's the same as 0.09, 9 100ths. The reason why I did that is because I know the square root of 9, and I know the square root of 100. Square root of 9 is 3, square root of 100 is 10. Since we're doing square roots of things, I'm going to make it plus or minus 3 tenths, or 0.3, 0.3. But professor, we have a calculator. I know you have a calculator, but some of this is a matter of if you can see some of these trends, you can save time when you're not plugging things into a calculator. Now this would be a quick one to do, yes. But as you've seen on the first exam, they're not always super quick questions to cover. So if you can see something like this, you can oftentimes find a more efficient way or just a quicker way and then save your other thinking time for other topics. All right. Square root of x to the 4th. Looking at what two things multiply to give me x to the 4th that are the same. X squared times x squared would give me x to the fourth. So I could rewrite this as the square root of x squared squared, because that's what times itself means. And then I see, square root of something squared, like we did up here. It will be x squared. Here we're splitting up similar to what we did up in the previous problem. Square root of 4 over square root of 9 will be plus or minus 2 over 3. Do I have to put plus or minus on both the numerator and the denominator? No, I don't. And the reason why is if I have a positive or a negative, positive or a positive, negative or a positive, negative or a negative, it's going to give me all the combinations. There really are only two answers when you say this. It'll just be plus or minus 2/3. Next one down, square root of 4/9 can be rewritten square root of 4 over square root of 9. So it can be done both together or separately. Still is plus or minus 2/3. And again, that's looking over here. When I'm only multiplying and dividing, again, only multiplying and dividing, I'm only dividing here. That means the roots can be split up over the division. Here we have only multiplying, so this can be split up as the square root of 9 times the square root of x squared. Square root of 9 is plus or minus 3. Square root of x squared is x, so plus or minus 3 times x, or just plus or minus 3x. Like we did in the first couple slides, find the cubes of the first 5 integers, 1 through 5, and then the cubes of the first -5 integers, -5 to -1. Remember, cube just means 1 times 1 times 1. That's the easy one. 1. 2 cubed. Just shout it out. 8. 3 cubed. 27. 4 cubed. 64. And 5 cubed. 125. All right. And again, these are going to be the most common cubes that we might see when we're doing problems. And the reason why I would use the most common ones is so that you can maybe get to something a little bit quicker, see some of those shortcuts. All right. -1 cubed. Again, -1 times -1 times -1 is -1. Next one down, -8, -27, -64, and -125. Whether or not you remember it, when going for, back in the day, if my exponent is odd, cubed is an odd number, that's 3, and this is negative, my answer will be negative. If my exponent is an even number, squared to the 4th, to the 6th, to the 8th power, something that's an even power, then my answers will always be positive numbers. All right. Now, with that said, what is the cube root of 8? What number times itself 3 times gives me 8? It's just 2. All right, the reason why it's not plus or minus, if I had negative 2 times negative 2 times negative 2, I would get negative, negative, negative. It would be negative 8. So over here, the cube root of negative 8 is negative 2. And this is where we get so quickly in the habit of thinking about square roots that we go, oh, we can't take a cube root of negative 8. Oh, no, we can. Odd roots can be either positive or negative answers. Even roots can only be, well, you cannot have a negative underneath an even root. The reason why I can, also I can look at this as this could be the cube root of 8 times the cube root of negative 1. 2 times negative 1 is negative 2. All right. And I'm intentionally writing it like that for a future slide, setting you up for what we're going to be getting to in a little bit. We're going to take a quick look and graph a square root function. Before we do it, as a reminder, if I had a squared function, let's say I had g of x equals x squared minus 4. All right, that's going to be a parabola. And at 2 and at negative 2, they're going to be zeros. How do I know that? Well, one, I look at this and say, well, this is x squared minus 4. That's a difference of squares. If I factor that, x plus 2, x minus 2, and I factor it, so I say, well, what makes this 0? Negative 2. What makes this 0? Positive 2. Those are my two zeros. 0 and 0, right there. 2, 0, negative 2, 0. And then if I were to put 0 in for my x, 0 minus 4, that's negative 4. That will be my vertex. So this ends up being a parabola that looks about like that. A square root function is going to be a parabola turned on its side. And while there are some algebraic techniques that would be great to know and understand and memorize, the reality is you're going to have a graphing function on your calculator or on your phone almost everywhere you go. But in a pinch, what can you do? Well, I'm going to put in numbers. I recall that I cannot, when I'm graphing real numbers, cannot have a negative inside of here. So if I put in 0, I have 0 minus 4. That's a negative 4. I can't take the square root of negative 4. So the smallest number I can use there is positive 4. 4 minus 4 is 0. What number times itself is 0? Well, that's 0. Then I'm going to pick another number up here, but I'm not just going to put in 5. Well, I could use 5 because that's actually not going to be a hard one to do. 5 minus 4 is 1, and the square root of 1 is 1. So right now I've got 4 comma 0. I have 5 comma 1. And now I'm trying to think, is it plus or minus? If it is, then I'm also going to have 5 comma negative 1. All right. The next number I'm going to choose is 8. You might say, well, why? Square root of 8 minus 4 is the square root of 4. And I know the square root of 4. Plus or minus 2. So then I'm going to have, didn't mean to put that underneath it, plus or minus 2. So I'm going to have 8 comma 2, 8 comma negative 2. And then if I go to actually graph this, xy, my first point is at 1, 2, 3, 4, comma 0. And at 5, I'm at 1 for 5, comma 1. And I'm over here at 5, comma negative 1. 6, 7, 8, 1, 2, 8, comma 2, 1, 2, 8, comma negative 2. And you'll see that it is a parabola turned on its side. I wrote the plus or minus in there because when I copied this over from my slide deck, the plus or minus and the square root did not transfer. There's apparently, I've got some font issues going on. Going back to, I can't remember what chapter of the book it was, function or not a function. This is a function. A function means for every x value, there's only one y value. And the method that we used to determine that was what's called the vertical line test. If I were to take a vertical line, let's see if I can make a vertical line. We'll make it red. We'll just do it as a vertical line like this. There it is. If I were to take that line, oh, it's gonna let me move it. And if I go here anywhere along that vertical line, it only touches that line, the equation, in one place. The blue thing is a function. When I go to the green, I'm like, oh, wait a second. Now it intersects both here and here. This or this is considered not a function. Vertical line test. A little quick review from much earlier in the semester. And these got all jumbled up when I transitioned over. So I'm just going to rewrite them here so that we can see them a little bit better. I'm going to take that first one down. And what we're going to do is here now, square root of 5. That square root, again, P-E-R-M-D-A-S. Back when we did multiply and divide, that we said they're inverse operations. If I divide by 2, that's the same as multiplying by 1/2. Right? If we were subtracting 3, that's the same as adding a negative 3. They can be rewritten one as the other. If I am taking the square root as an exponent, it is to the power of 1/2. So that next one down, the fourth root of 5 can be rewritten as 5 raised to the power of 1/4. How this becomes really helpful for you when using a calculator on a phone or an actual calculator, right? Actual calculator for an exam because we never use our phones. If I were to type this into my calculator to find, what is this actually as an approximate decimal? I would type in 5, and then depending on the calculator you have, you would then either, x to the y power is usually the button that's on your calculator. Then I would type parenthesis 1 divided by 4, end parenthesis, and then hit the enter, or in some cases, an equal sign. This gets you to show this. If you have a graphing calculator, you would type 5, comma, not the comma, sorry. You type 5. My commas there are just to show that you type this first. Then the next thing you would type on a graphing calculator is the caret button. And then you would do parentheses 1 divided by 4. If you know 1 divided by 4 is a decimal, you could have done that instead and just type 0.25. 5 to the 0.25 power. Then you hit equals or enter, and then it's going to give you an actual number. Now if I take the next one up there, and I'll just walk us through that, because it showed up reasonably well. If we were given this originally, and said to rewrite it without square root symbols, 4x minus 1, the quantity squared. First thing I want to make sure I don't do is I want to make sure I do not do this, because that would be wrong. Cannot, when there's adding and subtracting, bring the exponent into each piece. We can only bring exponents in up here. We can only bring exponents in when we're multiplying and dividing. Adding and subtracting, just having terms, this is not the same as this. This is very bad. Bad math. So instead, I'll just rewrite 4x minus 1, quantity squared, as itself. The whole thing is the fifth power. The fifth root. So that means the whole thing is to the 1/5 power. Now, I have a power, and the only thing outside of it is another power, so I have powers raised to powers. Powers raised to powers, exponents multiply. That'd be the 2/5 power. And that would be it. That would be done. This cannot be simplified any further. Again, because I'm adding and subtracting inside the parentheses, cannot bring the exponent in. Speaking of powers, just to recall, negative exponent means I take it and put it in the denominator. So 6 to the negative 2 is the same as 1 over 6 squared, 1 over 36. Again, just trying to mix in some of this review about exponent rules since we just did powers raised to powers. So again, the point mostly on this slide is the fact that we're defining how roots are related to exponents. Square root is 1/2 power. Fourth root, 1/4 power. Cube root would be 1/3 power. Now we'll do a couple examples here. Here I have things raised to powers. They're subtracting, which means adding and subtracting, I cannot bring these powers together, even though they're same bases. I can only bring them together when they're multiplying and dividing. However, out here I have multiplying. Z to the 2/3 multiplied by this whole set of parentheses. Going to use the distributive property. Rewrite it as Z to the 2/3 times Z to the 1/3 minus Z to the 2/3 times Z to the negative 1/5. Z to the 2/3 times Z to the 1/3. This minus, because it's in between there. Z to the 2/3 again, times the second term, Z to the negative 1/5. And my instinct should be to ask, can those simplify? In order to simplify, multiplying, write it over here again. Exponents and roots can only combine together when I am multiplying and dividing. Am I multiplying or dividing? Yes. So in what ways do those combine? Same bases multiply. Let's just do this for a second. Bring that over here. Same bases and multiply. Add exponents. Same bases and divide. I will subtract exponents. Powers raised to powers. I multiply exponents. Same bases, they're both base z, which means I can add their exponents. Z to the 2/3 plus 1/3 minus, right, add and subtract. These two will not be able to combine because they are going to have different exponents. So when I'm subtracting, I'm going to leave them as two different terms. And then here I'm going to, same bases, add their exponents. Z to the 2/3 minus 5. Two-thirds plus 1/3 is 1. So I'll have z to the 1. And I can write the 1. I typically don't. So if you don't have the 1, you don't have to. Then I'm going to have minus z. And then I have 2/3 minus 5. Well, that's just subtracting 4 1/3. Negative 4 1/3, I should say. Or you could write it as negative 13 thirds, negative 4 1/3. 3 times 4 plus 1, 12 plus 1, negative 13 thirds. Am I done? Yeah, more or less. I could rewrite this as z minus 1 over z to the 13th power cube rooted. The third power, the denominator, is my root, third power. 13 is the power on the z, and the negative means I put it in the denominator. Did like 3 steps there all in one. This is going to be, for the most part, preferred. The reason why is mathematicians, again, at some point in time in our illustrious past as mathematicians, decided we would rather not have variables in the denominators, especially if they have roots on them. So we said, hey, let's rewrite it so I have only non-rooted variables. So instead of writing it as the third root in the denominator, I write it as the 1/3 root in the numerator. All right, here we go. To simplify this, I'm going to use the process of FOIL. Firsts multiply x to the 1/3 times x to the 1/3. Outsides for O, 2 times x to the 1/3. insides, right here, will be minus, come on, 5x to the 1/3. And then the lasts, negative 5 times 2, negative 10. I have same bases. And I'm multiplying, which means I can add exponents. X to the 1/3 plus 1/3 is 2/3. Here, my variables are, there's my, middle terms are both x to the 1/3 power. Since they have the exact same variable, they can add and subtract. They can add or subtract. So I have 2 of them. I have negative 5 of them for a grand total of negative 3 x to the 1/3 minus 10. And then I always look to say, can I simplify more? Is this variable identical to that variable? No, they are not. This is x to the 2/3. This is x to the 1/3. The only reason why these two up here can combine is their variables are identical. X to the 1/3, x to the 1/3. This would be the simplified version of that up there. And then here, the next 2 items down, reminding us that just like we can split them apart, we can put them together. If I have square root of 5 times square root of 5, I get square root of 25, that's 5. Down here, square root of 4 times square root of 5 is the square root of 20. Once again, when I'm multiplying and dividing, I can bring them together for roots and exponents. Four to the 1/2 times 5 to the 1/2 is 4 times 5 to the 1/2. We usually did it the other way around, where we said, well, if I have 2 things multiplying to the same power, I can bring the power into each of them. Here I'm doing it the other way. I'm kind of pulling that out. So that's 20 to the 1/2. Which is as a half as square root of 20. What about that? Square root of 9 times the cube root of 8. Can they be combined? Does the square root of 9 times the cube root of 8 equal something the root of 72? Like, because 9 times 8 is 72. Can they be written like that? Well, I could look and say, well, this would be 9 to the 1/2 and 8 to the 1/3. What I did on the previous slide, I'd say, well, if they were the same, I could combine them. But when they're different, they cannot combine. So this is not going to be equal to 72 to some power. So if I were to, just like when we're talking about variables, exponents, roots, all of those things, in order for them to simplify by combining together, the roots have to have the same root in order to be multiplied together or divided apart. If they are different roots, square root and cube root, they cannot just combine naturally here. So instead, what I'd have to do is say, well, do I know what the square root of 9 is? Yes, that's 3. Do I know what the cube root of 8 is? It's one of our common cube roots. Yes, it is 2. Giving me 36. 6, not 36. 3 times 2. So being careful. We get rolling with this. We're like, oh, we're doing roots. We're combining roots. If it's a cube root and a square root, they cannot combine together into some other odd root of some type. Have to be doing the same roots. Simplified radical form. I touched on this maybe last class, the class before that one. It's a process of simplifying square roots. This is my expectation is from now on when we have square roots of numbers is that you will do a simplified radical form of them. I'll usually tell you and remind you, but when in doubt, simplified radical form. This is not doing it and plugging it into your calculator. All right, square root of 18. Simplified radical form is saying, all right, well, if I take those two, take 18 and split it into two square roots that multiply to 18. There's a lot of choices you could make. But what you're looking for is convenient numbers. That is there a number that I know the square root of? That's why we did all those squares. 1, 4, 9, 16, 25, 36. One of that first slides we did, right? 49, 64. Those are all my perfect squares. If I take 18, do one of those numbers multiply to get to 18? Absolutely. 9. 9 times 2 is the square root of 18. So again, I'm breaking that 18 down into two numbers that multiply to 18, but I'm choosing a number that I know the square root of. I know the square root of 9 is 3. And then I say, all right, now I've got this 2. Do I know the square root of 2? Nope, it's none of those. I know the square root of 4 is 2, but the square root of 2, I don't know the square root of it. Can I multiply anything to get to the square root of 2? Well, 1, I could say 1 times 2, but then I'd still have the square root of 1 times the square root of 2. The other way to think about it, once this gets to be a prime number, it just stays as the square root of 2. So the square root of 18 in simplified radical form is 3 times the square root of 2, or just 3 root 2. You can write it as multiply, or you can just write it as 3 root 2. 3 root 2 is the same as multiply. You're going to do the same thing with 72. This is where if you, trying to remember when it was that I had to memorize times tables. I think I was in 4th grade, maybe 3rd grade when they started making me memorize times tables. I don't know if they still do that anymore. I don't teach elementary school, never have. But are there two numbers that multiply to give me 72, where one of them, maybe both, at least one of them is one of these numbers up here? 9. 9 times 8 is 72. And we chose 9 because we know the square root of 9 is 3. Now we've got the square root of 8.
4.
Do we know any numbers that go into 8 that we know the square root of? 4. 4 is correct. It'd be square root of 4
And 2.
times the square root of 2. I chose 4 because we know the square root of 4 is
2.
2. Do I know the square root of 2?
1/2.
1/2 times 1/2 is?
1.
Yeah, 1/2 times 1/2 is 1/4.
Isn't it 1 over, well, square root of 2?
Nope.
Oh, I don't know.
All right. The square root of 2 is a number that 1 times what gives me 2? 2. So if I were to do that, I could split this up and say, well, this is the square root of 1 times the square root of 2. I know the square root of 1 is 1, but then I still have that root 2. Once I get to a prime number, I'm done. So that leg of my factor tree is finished at root 2. And then I take these, and I say, all right, square root of 72 is equal to, bring this down, 3 times 2 times 1, which I didn't have to do, times the square root of 2. 3 times 2 times 1 is 6 square root of 2. Sometimes people will say, well, I could take 72, do it this way, square root of 36 times the square root of 2. 36 I know is 6. Square root of 2 is prime, so this would then equal 6 root 2, which is the same as what we had down here. So sometimes you can get there quicker in some ways, and that's fine. You try the square root of 450. Now, I'm not sure what you did, but let's say you had no idea where to start. You could start by saying, well, I can split this into just two numbers, 45 times 10. Now, I don't know either of those as a square root, but then I can say, well, this is not 4. Square root of 5 times the square root of 9. This is the square root of 5 times the square root of 2. This one is the square root of 3 times the square root of 3. And once I get to all primes, I would say, well, look at that. I've got 2 square roots of 3. So those would simplify square root of 3 times square root of 3. These simplify to just the number 3. I have 2 square roots of 5. Square root of 5 times the square root of 5 is 5. 2 is left alone, so this would be 5 times 3 times the square root of 2, which is 15 square root of 2. Which is no different than if we would have started with a number that I know the square root of. Square root of 9. 9 goes into 45 5 times, and then there's a 0 there, so it's 50. That was 3. Oh, this is square root of 25 times the square root of 2. This is 5. 2 is prime. Still left with the same answer. 15 root 2. Because again, ultimately what we did is we broke that 450 into the square root of 5 times the square root of 5 times the square root of 3 times the square root of 3 times the square root of 2. 5, 3, 2. A lot of different ways of thinking through that question. Take a moment, jog your memories, look back at your notes. Solve that by completing the square. So if you didn't remember, the first step in completing the square, I want my variables on one side of the equation. I want my constants on the other side. So in looking here, this is a variable term, this is a variable term, because they both have t's. There's my constant term. So I need to move that to the other side. I do that by subtraction. Subtract 48 from both sides of that equation. 0 equals negative 16t squared, not 0,
Negative 48.
negative 48. 16t squared plus 32t. Step 2, I want the a term. If you can't remember what I'm talking about, up here at the top, I'll do it in a different color. 0 equals ax squared plus bx plus c. That's our standard form for an equation. The a term is the x squared term. The b term is just the x term. The c term is the constant term. A, B, and C. So when I talk about make the a term, a equals 1, I want this to be 1. So what can I do to this to make, how can I make negative 16 into a 1? What can I do mathematically that turns a negative 16 into a positive 1? Any ideas? Divide by negative 16. So I'm going to divide this by negative 16. But whatever I do to one term, I have to do to every term. So when I do that, I'll now have t squared. Because negative 16 divided by negative 16 is positive 1. Good, now I have my a as a positive 1. 32 divided by negative 16 is negative 2. Still have the t. On the left-hand side, negative 48 divided by negative 16 will be positive. Positive, what number? 3. Next step, I take half of the b term. That's my b term. I'm going to take half of b and square it and add it. Half of 2, because 2 is the b term, it's negative 2. So I'll put negative 2 in there. I take this whole thing and square it. On the left-hand side, I'm going to do the same thing. But what I'm going to do here is I'm going to quick move the 3 over. Plus 1/2 of negative 2, whole thing squared. On the left, I'll have 3 plus negative 1 squared. Negative 1 squared is positive 1. So 3 plus 1 is 4. On the right-hand side, I have t squared minus 2t plus negative 1 squared. And I'm going to leave it as negative 1 squared for a reason. I want a number that's going to multiply to positive 1, because that's what it's going to be, right? That adds to negative 1. Sorry, adds to negative 2. And if I want, I could actually, I could turn that just back into a positive 1 if I wanted to, right? Because I added 1. Added 1 to this side, so I added 1 to this side. I could think, I want two numbers that multiply to positive 1 that add to negative 2. The reason why I do complete the square up here, whatever this number is inside the squaring, half of b, half of negative 2. This value right here is negative 1. Half of negative 2 is negative 1. So what I'm actually getting is I'm getting what's called a perfect square. Perfect square is two things that are identical. It's a perfect square, which is t minus 1 squared. The purpose of doing completing the square, that's why it's called completing the square, is I'm completing it to make it into a perfect square. Something times itself. This term, same as that term, is half of b. So when I do half of b in square and add it to both sides, it allows me to have this and turn it into, not turn it into, it is a perfect square. I'm going to make this a little neater looking -1. Now I'm going to solve for t. There's my t, trapped inside the parentheses. The whole thing is being squared. So I'm remembering, well, how do I get rid of a square? Inverse of squaring is square rooting. This will be plus or minus 2 equals t minus 1. Add 1 to both sides. T equals 1 plus or minus 2. 1 plus 2 is 3. 1 minus 2 is -1. So my two answers are t equals 3 or -1. What does that mean? That means if I were to graph this function up here, it would cross the x-axis, or in this case the t-axis, at t equals 3 and t equals -1. It also means if I were to take this 3 and put it in for t squared, or t, sorry, so -16 times 3 squared plus 32 times 3 plus 48, it would equal 0. Solving for the given variable. Not sure why I put the Cartesian coordinate system on there. All right. What we're going to do, though, is... let's move that back where it was. Perfect. When solving for inequalities, especially when there's absolute value, I'm thinking, what makes this greater than 2? So here's the process. If I'm going to drop the absolute value, the other half of the equation goes on the left side. My sign points in the same direction. So this greater than or equal to sign is here. On the other side will point in the same direction, and on this other end I'm going to have -2. Because the absolute value means something inside there makes it positive. So when I pull that absolute value off, then I'm allowed to have a negative component. Then we're going to split this up into 2 equations. On the left, we'll have -2 greater than or equal to x thirds minus 1. On the right, I'll have x over 3 minus 1 greater than or equal to 2. I'll solve the left side first. Going to add 1 to both sides. -2 plus 1 is -1 greater than or equal to x over 3. All right, got to get rid of the 3 in the denominator. Multiply this by 3, which means I multiply the other side also by 3. 3 times negative 1 is negative 3, greater than or equal to x. On the right side, similar concept, add 1 to both sides. X thirds greater than or equal to 3. Multiply by 3, x greater than or equal to 9. Before I move on from this, when I multiplied, does that sign stay the same or does it change?
It changes.
Tell me why you think it changes.
Because it's swapped around. So we don't get it.
All right, say that again.
Because it's swapped around.
Swapped around
Or
or flipped. So here's what happens. If I were multiplying by a positive number, does the sign change here? No. I multiplied this by a positive number. Did this sign change?
no.
No. So if these signs don't change, this sign doesn't change. If I were to multiply by a negative 3, would this sign change? Yes. If I multiplied this by a negative 3, it'd be no longer negative 1, it'd be positive 3. So if the signs change, then that sign changes. So when I multiply by a negative or divide by a negative, then the inequality flips its direction. I know why I put this on here. So then I've got two values. I have over here 9 and over here negative 3. I have the line underneath tells me it could be equal to at negative 3, which means at negative 3 I have a closed dot. At positive 9 I also have a closed dot. Again, because greater than or equal to. X greater than or equal to 9. Greater than is up this way. Negative 3 is greater than x. Well, there's the negative 3, and if negative 3 is larger than x, then I'm talking about shading to the left. Now, if you can't see that the way it is, then my recommendation is like, well, you can rewrite this in the backwards order. So instead of saying negative 3 greater than or equal to x, I could rewrite it as x less than or equal to negative 3. Again, I just took it and wrote it in exact reverse order. X less than, smaller end, negative 3. X less than, negative 3. And if I were going to do this in set notation, I would be negative infinity up to negative 3. That's a bracket. It's a bracket because it includes 3. Think of it like as a saucer versus a deep bowl. Stuff can spill out, negative infinity. It's never quite, you're never going to quite get to negative infinity. But here you can get up to exactly 3, negative 3. Or 9 up to positive infinity, bracket in parenthesis. That's set notation. And the reason why I say or is because I cannot be here and here at the same time. You cannot be less than negative 3 and greater than 9 at the same time. All right, those are the check your understanding. So in your modules, we'll look at that here in a second. All this information is there.